Look at this pure kinematic model. It dictates motion purely through geometry. We command the robot to move, and it accelerates to top speed instantly. We tell it to stop, and it freezes perfectly on its target. This is standard behavior in baseline simulations. We apply a sudden start, followed by a sudden stop, and math executes the command flawlessly. But when we test that exact same command sequence on a physical differential drive robot, the result is completely different. The robot overshoots the target point. Instead of an instantaneous halt, it carves a curved deceleration profile as it slides to a stop. The kinematic equations assume perfect rolling contact and zero mass. They ignore physical realities, like uncompensated mass, rotational inertia forces, and surface friction. A pure kinematic model is a geometric illusion. To build a reliable control system, we have to bridge the clean math of idealized vectors with the messy, resistant reality of actual physics. We need a dynamic model. Building that dynamic model requires accounting for all forces, but applying traditional Newtonian mechanics creates an immediate computational bottleneck. The Newton-Euler approach requires us to compute the explicit vector forces acting at every single joint and wheel axis. The control loop wastes processing power calculating internal constraint forces, only to algebraically cancel them out at the end. We bypass those vector calculations entirely by using the Lagrangian approach. Instead of calculating directional forces, this method uses a single scalar equation based on energy. We subtract the system's potential energy from its kinetic energy. Applying the calculus of variations to this difference yields the Euler-Lagrange equations, producing our equations of motion directly in generalized coordinates, without ever computing an internal joint reaction force. By shifting our mathematical perspective from directional vectors to scalar energy, we systematically derive clean, actionable dynamic equations for any robotic architecture. This diagram shows a differential drive robot's coordinate frames, the fixed world frame, and the moving body frame pinned to the robot. Motion is determined by the left and right wheels, but their design prevents the chassis from sliding sideways along the y-axis. We define this no lateral slip rule mathematically as a non-holonomic constraint. Specifically, negative x dot times the sine of theta plus y dot times the cosine of theta equals 0. This constraint involves velocities. It cannot be integrated down into a static position equation. Because of this, pure kinematics alone cannot capture the robot's reachable state space. It is mathematically trapped by its own wheels. Our dynamic model starts with the Lagrangian. L equals kinetic energy, T, minus potential energy, V. On a flat surface, potential energy drops to 0. The remaining kinetic energy splits into two components, the chassis' translational energy and the robot's rotational inertia. Here we face a mathematical conflict. We have our energy equation, but we must rigorously enforce that non-holonomic constraint. To bind them together, we introduce Lagrange multipliers, denoted by lambda. We insert these multipliers into the Euler-Lagrange equations to represent constraint forces. By substituting the constraint equation back in, the lambda multiplier is entirely eliminated. This maneuver strips away all the unknown constraint forces acting on the wheels, leaving a clean dynamic model tied to the robot's center of mass. It is now perfectly ready for control design. Applying Lagrangian equations yields the standard form of robot dynamics. M of q times acceleration plus Coriolis plus gravity equals joint torques. M of q is the inertia matrix, extending into a symmetrical grid containing mass and inertia for both the chassis and wheels. By definition, this matrix is symmetric and positive definite. That mathematical property guarantees that our dynamic equations are always well posed and invertible, meaning we can reliably calculate the required torques for any desired motion. Remember the robot failing to stop instantly? The mass and coupling inertias inside this matrix dictate the exact mechanical resistance against sudden velocity changes. The inertia matrix is the mathematical embodiment of physical momentum. It prevents instantaneous acceleration, causing real-world robots to overshoot their geometric targets. Modeling the inertia of the chassis provides a theoretical mass to move. To complete the physical model, we must define the limits of the hardware doing the moving. Standard DC motors operate under strict electromechanical constraints. Back EMF caps the motor's top speed, while thermal and current limits restrict its maximum stall torque. We then subject those motors to ground interaction losses using a combined friction model. Coulomb friction captures the static breakaway force required to start moving, while viscous friction accounts for velocity-dependent drag. When we integrate these friction coefficients and motor limits into our dynamic equations, the perfect geometric lines of the kinematic model break down into a realistic curved deceleration profile. True dynamic modeling requires compromise. We have to marry the clean inertia matrix with the gritty, energy-draining reality of electrical bottlenecks and tire friction. If we feed open-loop commands into the system, instructing the motors to spin at a fixed voltage for 5 seconds, the robot will drift. Uncompensated friction and inertial momentum accumulate over time, pulling the chassis off course. To follow a complex trajectory like a figure 8, we implement closed-loop proportional control. The system measures position against the target, calculating error in real time. By employing look-ahead targeting, focusing ahead of its current position, the algorithm anticipates curves for smoother steering. To ensure stability, the controller applies velocity saturation. This mathematically clamps the calculated outputs, preventing the control loop from commanding torques that exceed the physical limits of the DC motors. Closed-loop control acknowledges the laws of physics and actively fights them. It relies on continuous sensor feedback to drag the heavy, friction-bound chassis back into alignment with its mathematical target. This mathematical battle between control and physics plays out inside simulation software. An environment like Gazebo parses XML-based URDF files to determine exactly how a robot should behave in a virtual world. If an engineer omits the inertial parameters in a URDF description, the physics engine will treat the links as massless. The dynamic simulation will collapse into numerical instability, ruining the accuracy of any control algorithm tested on it. The theoretical equations derived from the Lagrangian method map directly to software. The formula calculating the rotational inertia of a wheel translates exactly into the inertia IZZ parameter inside the robot's configuration file. Because manually recalculating these values after every hardware change invites error, developers use Zacro macros. These parameterize the equations, allowing the physics engine to automatically update the inertia matrix whenever the chassis mass or wheel radius is modified.